Good afternoon. I am Emanuele Borgonovo, the director of the new Bachelor in Economics Management and Decision Sciences of Bocconi University. And I am very glad to welcome you here at this second BEMACS talk. I am very pleased and honored to have here Gary King, who is a full professor at Harvard University. He's actually the Albert J. Weatherhead University Professor at Harvard. He's also the director of the Institute for Quantitative and Social Sciences. He has written several papers in which he shows the use of statistics and numbers in helping social sciences and policy, and several of his works have had a strong and very high influence in both the scientific and professional communities, and several of his works have appeared in journals such as Science, for instance. And I'm also very glad to have here Professor Sonia Petrone, who is the director of the PhD program in statistics of Bocconi University, and she's also the president of the International Society of Bayesian Analysis. Actually, she's past president because she was president last year. So, and here I've already seen several interesting questions asked by you who are following. One is in fact very close to the questions I would have asked for a start to Professor King. And the question actually sounds, aren't social scientists and quantitative methods, social sciences and quantitative methods an odd couple? Do we really need numbers to understand people? So better than Gary King, probably no one else is allowed to answer this question, so I'm very glad to leave the floor immediately to him.
Thanks so much, and thanks for having me. Thanks for everyone watching. Are in social sciences and numbers an odd couple? Do we need to understand people with numbers? No, you can understand a person without numbers. Of course, you walk into a room, you introduce yourself to someone else, and you can understand them. But how are you going to understand what millions of people are saying or doing or thinking? If you want to do that, then there pretty much isn't any other way. Let's take social media, for example. So social media is perhaps the largest increase in the expressive capacity of the human race in the history of the world. It enables one person to write a social media post, and at least potentially billions of other people could read it. It's one-to-one communication, or one-to-many communication. However, suppose you're interested in what billions of other people are saying. There's no one person that has the ability to understand what billions of other people are saying, because you can't possibly read all that information all by yourself. So the only way to understand what everyone else is saying is through some type of quantitative analysis of all of that text. So if you want to know what people say, then you have to use numbers in some way. And that's just one thin slice of the areas in which data can provide some value for people.
Okay, and Professor Petrone?
Well, maybe I could add to that. I do agree, but numbers don't speak by themselves. So we will always need the right combination of qualitative knowledge, information from the experts, and an intelligent use of the data and of the quantitative analysis. At least this is what statisticians try to do, being able to work with the experts and interrogate the data with the right questions and try to give the guidance of the way we can exploit information, make educated, sound prediction, and give a guidance to the right decisions. So I think it's always a combination. It's not an odd couple, but maybe a successful couple.
You know, just to add to that, one way of thinking about it is that there's a continuum from fully human to fully automated. And fully human just does not scale. It's not possible with just one person through the abilities that we have to read and see and understand to understand and take value from massive quantities of information. So fully human doesn't scale. But what about at the other end of the continuum? Fully automated, completely quantitative. Usually that's pretty dumb. So a fully quantitative analysis, that's like an Excel spreadsheet with no column and row labels. It's just a bunch of numbers. It wouldn't do anything. So the thing that Sonia's talking about is computer-assisted quantitative analysis, or human-led, or human-empowered quantitative analysis. That's what tends to work the best. One way of thinking about it is, if you're out there and you're doing something, whatever it is you're doing, you might as well have some help. And if we can provide some help through these techniques, then that's terrific.
There is another new challenge, I think, with this web revolution era, the speed. So social behavior is changing very fast. We are living a revolution which is exciting and challenging at the same time. And we have to rely on some computer-assisted way of analysis, online learning. So we have to get our hands in the technology and be able to understand the transformations going on, trying to predict where we are going and try to make intervention. And so this is not possible in none of the extremes that you were outlining, no?
Yeah.
But this issue of speed is something that I think it's new in our era, no? And this cannot be done by only human being, not only without the data, without the capacity of analyzing quickly the data, with the sound question, with the right questions. So data don't speak by themselves, we always say that. We need to have the right question, and we need the technology for analyzing in a quick way and in a sound way this huge amount of data, even a little amount of data.
Yeah.
We always need human intervention, a combination of this.
Yes, yes. This relates also to a question that appears there, and then we are going to ask, and also to a news that appeared yesterday on one of the main Italian newspapers, that MIT invented this data machine, big data machine that is capable of automating data analysis much faster than what humans do. And actually, we have a question there. Nowadays, how much value added can the analyst extract from data process that big data approaches? So then, this is a question for you. Can machines, data analysis adds value, also in politics, and you will give us some examples. Can the machines do better than us, and what is the value added of this?
So maybe we could put it in context. In context, we could ask, why are we here? Why do we get to speak to you? And I think the reason is that there was some journalist that invented the term big data. And because once that term was invented, that seemed to resonate with people, and they seemed to understand that something big was going on. And I think it's terrific that there is this term and that everybody understands it. That way, my folks now, they think they understand what I do, which I'm really thankful for. But in fact, the revolution in big data has nothing to do with the data. Well, almost nothing to do with the data. Data is cheap. Data. If you work in a company or you're in a university, that institution produces data. At the end of the year, it's going to produce way more data than at the beginning of the year. If there's an HR system, a human relations system, or a finance system, or almost any other type of computer system, they'll replace it, they'll upgrade it. And when the upgraded system is there, there'll be a little spigot that comes with it, and that spigot will have data pouring out of it. And so doing almost nothing, there's more data. But what does more data help with? Actually, it doesn't help with anything unless you know how to extract the information from it. So you need the people. You need the people to develop the analytics. Big data is not about the data. Big data is about the amazing inventions of statistics and data science that make it possible to extract information for people from information, from data, no matter how large the data are.
Yes. Okay,
The question was if you can have something automatic.
Automated, yes.
Yeah. So there is actually is a colleague and friend of mine in the machine learning group in Cambridge, and they created a software where you put your data, they make your statistical analysis for you, and they even produce a text file with plots and design. Statistician hated that, no? Because, well, you're stealing us the job. Luckily, I don't think they're going to steal anything. I mean, we are happy if there are tools for speeding up our job, for doing like routine analysis. That's good. But as you were saying, Gary was saying, there will always be the need of people doing asking the right question and finding the right algorithm, making sense of the mess, data don't speak by themselves. I keep saying that. Yeah.
It's definitely true that more and more jobs are pieces of jobs that are boring or routine or rote are amenable to automation. Some of what we do is amenable to automation. Anybody that has pieces of their jobs automated and it produces change, that's a little worrisome. But if everything is set up appropriately, it ought to make for a better life.
Yes, yes. And so today in your seminar you were discussing application of the use of statistics and data to decide health policy for the whole state of Mexico. Can you tell us about some of your experiences using data to influence politics and policy making?
Oh, sure. So in Mexico, they passed a law that gave health care to 50 million Mexicans that previously had no health care. And the government wanted to make sure that the program that was being implemented would actually do the job. The fact is the vast majority of programs like this around the world don't actually make it to the poor people that need it. Officials get nicer cars and buildings, and everybody's trying very hard, but it doesn't actually make it there. And they wanted to actually verify that it was going to be there. And so they made it possible for us to do a giant randomized experiment where we could figure out the actual causal effect of implementing this program on the people. And the result of it was quite amazing. The program did seem to have an effect, quite a big effect. The money actually made it to the people in places where it was deserved. But we also learned many things that the government didn't know and nobody had any idea about. And just learning those things made it possible for people to get health care when they wouldn't otherwise, to literally live longer lives. So one example is people had to sign up for this program. So in order to sign up for the program, you had to go somewhere and sign up. However, the program was designed for poor people. So the poorest of the poor, they were automatically signed up, which was terrific, what you would think. However, these people weren't, we learned that they were not aware that they were being signed up for the program. And so the states which got the money to implement the program got all the benefits of the money, but they didn't have any of the costs because people never sought health care. So all we needed to do, and all we did, was just reveal what the results were, which is that there was a whole class of people that weren't aware of this program, and then they just made it available, and then all these people got health care when they wouldn't have otherwise if it weren't for this evaluation. So throughout many governments all over the world, governments are recognizing that most public policy programs are gigantic experiments with no control group, with no way to figure out whether they have an effect or not. If you put a little bit of design and a little bit of public policy evaluation into the design of and implementation of the program, it's possible to improve the program along the way and to learn enough so that it is possible to make the program better and better. And so that's just one example, but there's many other examples in many governments.
Well, thank you very much. And so another question that we read there is descriptive statistics are fun to know, but to what extent do you think it is possible to predict one's behavior at a single individual level? So can we use statistics to go? I think that's an interesting question.
Well, you know, one of the big challenges and goals in medicine, for example, is to reach personalized medicine. So where we want to give to individual specific therapy to people. So if the question is, can we go beyond the average individual and can we adapt and use the information? Because remember, statistics is a science for organizing information, exploiting information. So every time there is the need of using information, there is statistics. And the doctors need the information, and it used to be on the average individual. But nowadays we have the tools for targeting this. For targeting, taking into account individual variability, or even going to the individual DNA. So we had this, the big challenge for science, I would say, for statistics for sure, has been the Genome Project since the 1990s, where scientists to decode the human genome. which means very individual specific information. And also big data again, but also a mass of information. You have all of this information on microarrays and DNA and genes, gene expression, and we need to organize information to look. We need the right questions to find the right answer, to find the gene that is responsible for cancer, and to be able to give more and more target therapies. So if the question was, can we go beyond the mean and to individual specific? Yes.
It's also, it's a great question because it highlights the kinds of things that we do. Obviously, we don't want to treat every individual the same way as we might the average. And there are differences among individuals. But there's also a lot that's the same. We all feel that we're individuals and we're distinct and there's something special about us, and there is, but there are also a lot of things that we do in common. Think of, or even that we do the same every day. So think of where you were today, at every moment today, and then where you were yesterday and where you were the day before. I think if we had that information, we would be able to predict with pretty high probability where you're going to be an hour from now. That doesn't mean that you're not unique and you're not special, but it means that you follow certain patterns and you have certain habits. And because of social science's ability to understand the behavior of individuals, we know that about people. We know that people follow certain patterns and habits. Then it's the job of the data scientists to find those patterns in ways that might help you. So.
Finding what is common, what is individual specific. Use all the information you have. When I do Bayesian statistics, which really means everybody is an individual, and I want to use all the information I have. Data, information from the experts and everything. But now that we have big data from the web, and we can really follow individuals. We can track my choices in choosing books or films or movies, and on the average, everybody is able to act. I can target the average individual. The challenge now is to target the tails, to target very very specific behavior, because with the technology, with the data, the amount of data we have, somehow targeting the average is done. Mm-hmm. And the issue is, can we target the extreme values, the extreme behaviors? So, but again, is a matter of balance. What is in common? What are common patterns? And what are the interesting individual ones? Mm-hmm. No?
Yes.
Yeah.
Yes. And then tail events are really a problem in all science.
Tail events and not tail, but maybe. Not average individuals, maybe yes. Interesting individuals, because they are not like the mean.
Yes. No, a curiosity out of maybe, even if now we come into a big, more technical question, because you have worked a lot also on text recognition, so on understanding trends and what is happening even in this moment, maybe analyzing texts in tweets and so on. So can you tell us a bit what's this magical about, taking 3 million tweets and trying to understand, a pattern or something which is happening now in society?
Right. So the general issue is that it used to be data analysts could only analyze things that were obviously data, columns of numbers. And what we've realized over time is that there's many other sources of information that can be made into numbers and therefore are amenable to analysis by our methods, and therefore we can provide some value. So text is one example. Other examples, by the way, are audio and video and other or geographic location, satellite imagery, many other types of images, many other types of information. So text is one it's uniquely human, it's uniquely personal. And there's a massive amount of information about it. I talked about social media earlier. Today, there will be 650 million social media posts that are available to you on the web that were written today. So I don't know how you're going to understand what all that is, but if you use the kinds of methods that we've been discussing, you could actually understand what that's all about. So we developed some technology that was commercialized in a company called Crimson Hexagon, which Harvard licensed the technology that we came up with and patented it and licensed it to the startup that I helped create, actually. And what it does is it tries to find, in this case, the average. So sometimes, as we were speaking, we really want to know about the individual. But sometimes, yeah, but sometimes we only want the pattern. For example, no one cares what StatPumpkin222 says on Twitter, right? We don't care what any one person says. We only care what everybody has to say. And that's something that we're actually very good at. We can understand how that works. So that has been that has been attempted in ways by taking individual social media posts and putting them into categories. So what are the categories? The categories may be the features of the iPhone that you don't like, or the features of candidates that you like or don't like, or how much you like the candidates. They could be any set of categories. But remember, what we really care about is not taking one post and putting it in one of these categories. We care about the percentage of all the posts in these categories. So the first methods that were used to understand social media posts were classifiers. They were the kinds of things that would automatically put posts into categories. But the best that they could do was maybe 60, 70% accurate. So if you're 60 or 70% accurate, what that means, of course, is that you're 30 or 40% inaccurate. And if you're interested in the percent of the posts in a category, such as the percent of people that like a candidate, and if that number is 20%, but you're 70% inaccurate, so you estimate it to be 20%, but you're 30% off, then the truth might be 20% plus 30%. And so the truth might be 50% instead of 20%. So in other words, even if a classifier is the best one that there is, it still might give useless information for our purposes. So what we developed for this technology was, was something that didn't try to classify individual posts, because for this purpose, we didn't care about any one post. Instead, what we did is we tuned it to estimate the percent in a category. And so that we can get, and it will work basically exactly right on average. We've done, and in fact, just to add to the story, this method, which optimizes the percent in the category rather than the individual classification, works in one case, doesn't work in another case. It came from a completely and utterly different application. So the application that we had originally didn't have text, it didn't have social media. In fact, it didn't even have any live people, it had dead people. So what was it? It was trying to estimate the percent of people that are dying of different causes in most of the world where there are no death certificates. So how do they do that? So the way they do that is you can't do autopsies in most parts of the world because it's culturally prohibited. So instead, they go into houses where someone died and they ask a series of difficult questions about the symptoms the person had before they died. And then there's an individual classifier applied. The first individual classifier was a doctor. You give the answers to the questions to a doctor, and the doctor would say, oh, the person died of malaria. But what everybody discovered was if you give the answers to a question to a different doctor, they would give a different cause of death. So the individual classifiers, that is the doctors, were useless for this particular purpose. Then they tried to automate that, and they used the best automated classifiers. And the best automated classifiers could only get to 70 or 80% accuracy. But that's 20 or 30% off. If you get that 20 or 30% in one category, you could completely produce no useful information. So we used this method that I described, which was tuned to get the percent in a category correct, even though it didn't really do any individual classification. Because we didn't, I mean, in public health, they don't care about anyone, they only care about everyone, right? So that's their goal. Their goal is not to find out how one person died, they only care about how, what the trends are. Because if people are dying from one cause rather than another, then we could devote more dollars to try to solve that problem. So we just recognized at one point that the solution to this problem was the same mathematically as the solution to understanding what millions of people were saying on social media. And so we applied it and it worked in that case too. That's the power of data science.
And then I think that your solution also had another clever feature, that it was simple and fast, wasn't it? I mean, I don't know, that as far as I can know about what you do. So, because the problem is somehow a classical problem also in statistics, so understanding the proportions. But I think you had also the way of doing this in a simple, sound way and fast, because this is a challenge when you have a lot of data. You want a sound solution that is simple but sound, and also fast to compute and to communicate. No? So one has to be clever and have a clear view, again, of what is the interesting question to ask. And because, you know, in the problem you are describing, you are interested in understanding the proportions. But if I have to, if I wanted to have, say, an efficient email system, I want an efficient spam classifier. And then again, I'm back to the issue of classify each message, and I want a good classifier that is able to say this particular message is spam or is not. So again, different problems, different questions, different solutions, always needing the statistician or the data scientist.
And I think we are almost closing in terms of time our talk, but we can close with answering one of the questions that we did not answer last time, and it was about if it's going to be lots of exciting job in big data in the next 5 years, and I think the question from what we have discussed is clearly yes. You see the number of applications in which these type of competencies are needed, and
Don't forget
climate change. And in fact, so I will leave these last sentences to Professor King and Professor Petrone just to confirm that this type of professional figures are indeed needed in the market and in several fields.
I mean, in my experience, there has been no unemployment in this field in over 3 decades. So we'll have to make a prediction into the future about the proportion of people that need to that will be unemployed in this field. But my prediction is it will be very small. So.
There are ranking nowadays of what are the most successful, say, well, I'm director of the PhD in statistics at Bocconi, so I'm ranking what are the most successful and best paid PhDs in the world, and they say PhD in statistics. Statistics, data science are somehow 2 names for the same job and profession. And everybody says, Hal Varian in Google says statistics or data science is the sexy job of this millennium. And well, everybody is saying we need, so we cannot keep our students because they are stolen by Amazon, Facebook, Google, and so there is definitely a need for the analysis of statistician, data scientists for analyzing the data on the web, big financial data, climate or public health. I think it's, everybody says this, I want to say this, it's a very exciting time to be a statistician and a data scientist. I want to say something to the young students. Follow your dream. Maybe somebody said something similar. But do follow your dream. Have a dream. You are young, so be enthusiastic. Follow your dream. Have a dream. Don't be overwhelmed, however, by the pressure to success, to study in the right places, to do successful things. Just follow your dreams. Be relaxed. And do consider to become a data scientist, a statistician.
You know,
yeah.
If I could just add, data science, there's a lot of ways of contributing to data science. Getting a PhD in statistics with this person would be an excellent idea. But there's
Don't tease me.
But there's many other ways as well. Data science is really the combination of 3 things. It's statistics, it's computer science, and it's the domain expertise in some particular field. So you can go into a vast array of fields and specialize in the methodological subfield of that field and connect with all the data scientists across fields. So within economics, there's econometrics. Within political science, there's political methodology. Within psychology, there's psychometrics. In public health, there's biostatistics. There may be 100 of these separate fields. And understanding that fact, and that pretty much whatever field you go into, there's going to be some methodological subfields, and also understanding that those fields are connecting more and more, that's what the data science movement really is.
Okay. Thank you very much, Professor King and Professor Petrone. Really thank you for coming here. And I say Thank you to all of you who have watched us and listened to us, and I take the occasion to also send you the best wishes because this is the last appointment of 2015, so all the best for your 2016 and the incoming holidays. See you in 2016.
Thanks for listening.
Ciao, ciao.